Hello everyone, welcome back. So in the last lecture we introduced the basic operators A and A dagger, and we said that we have a commutation relation between them. A and A dagger commutator bracket is 1. Similarly, we derived some relations, right? So just today in this lecture we'll try to understand what is the physical meaning of these operators, and then what happens, how that can be used to actually derive the eigenvalues of a quantum harmonic oscillator. So just to recap, so we introduced this A dagger and A operators. We don't need to worry about the functional forms, and I'm not putting the hat notation, but it's understood that these are operators, okay? Or if I want to explicitly say it, I should always say A dagger cap is equal to 1. We showed that in the last lecture. Similarly, we also saw what happens when Hamiltonian acts on A. This is going to be equal to minus h cross omega A hat. And Hamiltonian acting on A dagger is going to give you h cross omega A dagger. Okay, this is the thing what we have seen. Now, we want to understand how the operators impact the energy eigenvalues. So what is the equation that gives us energy eigenvalues? Hamilton's, basically the Hamiltonian, right? The wave equation, Schrodinger's wave equation, that I can express as h, let's say, psi. So Hamiltonian acting on, let's say, psi n is going to give me the energy eigenvalue En, and the wave, so psi n is a wave function, right? It's eigenfunction essentially. Okay. Now let us see what happens if I apply a lowering operator. Okay, sorry, I'll apply. Okay, so let's see what happens if I apply Hamiltonian on A psi n. Okay, this is what I want to find out. What is this? How can I do that? Well, what I can do is I'll add and subtract. So I'll add and subtract psi n, rather I'll add and subtract A h psi n. Okay, so basically h A psi n minus A h psi n plus A h psi n. What will we get? So immediately you see that these two terms are the commutator bracket. So what I will say is h A minus A h psi n plus A h psi n. Hamiltonian acting on wave function will give you En psi n, right? So that immediately I know what is the commutator bracket for h and A. Okay, so I know that this thing is going to give me minus h cross omega A and psi n, correct? So this will be minus h cross omega A psi n plus En A psi n. Okay, so that essentially gives you En minus h cross omega and then A psi n. This is what I'm getting. Okay, so what we find is when h, okay, now I'll write it in the operator form, basically A cap, or rather h A psi n is going to be equal to En minus h cross omega into A psi n. So what this tells us is that this A psi n, it's an eigenfunction. A psi n is an eigenfunction of Hamiltonian with an eigenvalue of how much? The eigenvalue of this is the coefficient here. So this is my En minus h cross omega, eigenvalue of En minus h cross omega. Okay, this is my this is how, let's say, Hamiltonian acts on. So this is the impact of the operator A on psi n. Okay, so what we'll say is, you have a question? No? Okay. So this is what I have finally captured here. Sorry. So, okay, let me just recap that. So this is going to be equal to En minus h cross omega and A times psi n. Okay. So that is why I will call my A operator, A hat, as lowering operator. Okay. Because when it acts on the wave function of a particular n, it is actually giving you a lower eigenvalue. Okay. So when A acts on psi n, it gives lower eigenvalue, and that I'll call it as En minus h cross omega. Okay. Now we have one more operator. For obvious reasons, you will see that it will actually turn out to be the raising operator. So how will we see that? So if I think of H A dagger acting on psi n, I can simply add and subtract. So H A dagger psi n minus A dagger H psi n plus A dagger H psi n. Right? So this is going to be my commutator bracket. So this will be, I'll make the story short. So this will, rather H comma A commutator, H comma A dagger acting on psi n plus A dagger H acting on psi n. So this will be H cross omega plus En acting on A dagger psi n. Right? So that's why, so I'll call this as A dagger as raising operator. Right? So now, what is it doing? Well, when A dagger acts on psi n, it gives you the higher eigenvalues. So En plus H cross omega. Okay. Remember, we are talking of quantum mechanical, we have to derive the expression, right? N plus half. We will get to that. Okay. So now what's happening is, let's consider, let's say an eigenstate, consider eigenstate psi n with eigenvalue En. Okay. So now that's what I'm considering here in the center. En has an eigenvalue psi n. Now if I operate A on that, lowering operator, the eigenfunction comes lower, and then you get the eigenvalue En minus h cross omega. If you operate it the second time, so essentially if you do A acting on psi n gives you a lower wave function, right? Eigenvalue of En minus h cross omega. If A acts twice on it, so basically A square psi n. So if A acts twice, you essentially get En minus 2h cross omega, and so on. So you see that is what is shown in this ladder here. So you have psi n corresponding to En, and A acting on psi n will give you En minus h cross omega. A acting twice will give you minus 2h cross omega, and A dagger acting on psi n will give you E plus h cross omega twice, and so on. So essentially we are having this sort of a ladder that is built up, and the spacing between these operator levels is h cross omega, any two levels. Okay. So if I want to talk of a general eigenvalue, what will that be? N plus half. So basically in this case, h of psi n is going to be equal to n plus half of h cross omega psi n. Correct? This will be the generalized eigenvalue. Okay. When you have, it should have been flipped. Okay. So in this case, this is h acting on psi n is giving you this. H acting on A dagger psi n is giving you En plus h cross omega twice, and so on. So basically H acting on psi n will give you n plus half into h cross omega plus acting on psi n. So we can clearly see that psi n is an eigenfunction, which of course that's what we have considered right in the beginning. But the energy eigenvalues are En is equal to n plus half h cross omega. Right? So the beauty of this is, without really considering any of the details of the potential, how the solutions will look like, just by using this algebraic technique. So what did we do? We simply took the original Hamiltonian. We saw that it was p square plus some x square. So we said, okay, we'll factorize it and we'll try to find solutions for that. Because see, how do you solve a second order differential equation? Or not differential equation, second order polynomial equation, ax square plus bx plus c. What is the technique we do? We factorize it. Equal to 0. X equal to this, y equal to this. That is the solution we take. So now what Dirac did was, just to recap, so he saw this, and he said, okay, let me try to factorize it similarly. Okay, since it was x square plus y square, he said, okay, the plausible solution will be x plus iy into x minus iy. So that should give me some sort of solution. But when he did that, you see that, okay, no, this is not, this is the a dagger is not equal to a dagger a. There is some additional term coming in, that is energy. So you just do the algebra, operator algebra, nothing. It's a very simple algebra. You just have to be careful in which order you are applying the equations. As long as we are careful, we can actually see that it will work out. Okay. So now we did all that. We got to certain relations which are basic, kind of, we can say these are the derived equations. Okay. Just simple algebra. And then from that, by looking at how these raising and lowering operators behave, we are able to get to the solution of the quantum mechanical harmonic oscillator. So these are the eigenvalues of light, essentially. That's what we said, no? In one of these earlier lectures, we said this is a solution. But now we said, oh, this is n. When n equal to 0, it is the vacuum state, which energy h cross omega. If you have 2 photons, 3 photons, if you have 10 power 15 photons, it merges with the classical value. That's what we have shown. So now we have derived that. So this is the foundation. That's why I said, whenever you're dealing with quantum photonics or quantum optics, you cannot escape these raising and lowering operators and wave functions and so on. We'll have to bite the bullet at some point, and that's what we did here. All right. So I hope it was okay. So now we just, before I close for this week, I just want to do one more small thing. We said A acting on psi n will actually lower the energy. What happens to A acting on psi naught? If you go to the lowest energy, psi naught means I'm talking about this psi naught is essentially my ground state wave function, correct? This is my ground state wave function. So what should happen if I have a ground state wave function? It should be 0. There's nothing else below that. Okay. So what we are saying is A acting on psi naught should give me 0. So what I'll say is I have my operator A. Okay. This is my definition of an operator A. Acting on psi naught should be equal to 0. Now, what we said was, when you know the wave function, let's say psi 0 wave function, you can keep applying the raising operator A dagger, and you can find all the other wave functions, and you'll also get the eigenvalues. You just need one wave function, whether it's psi 0 or psi 1, psi 2, whatever. No, we just need one wave function, right? So that the reason, the process for getting that is by solving this equation. So I have a differential equation here. You see that it's a differential equation, right? So basically what we are saying is this is a bunch of constants on the side. Ignore that. Okay. Let's say we have to solve essentially m omega x cap plus I p hat psi 0 equal to 0. This is what I need to solve. X cap operator we are very familiar. So m omega x cap is simply x, right? But momentum operator is minus I h cross dou by dou psi, acting on psi. Minus and I square will essentially become plus. So plus h cross dou psi naught divided by dou x equal to 0. Okay. So what is my solution here? Sorry, my differential equation I need to solve is I'm sorry, I should also put a psi naught here. Okay. So the differential equation I need to solve is dou psi naught divided by dou x is equal to minus okay, let me do a little bit of, let me clean it up. So this is my ground state wave function. So then I can delete this thing, cut, and then I'll take this up. So I'm just creating some space. Okay, so now my differential equation is dou psi naught divided by dou x is equal to, it goes other side, so minus m omega x divided by h bar psi naught. This is my solution. So what sort of equation will actually satisfy this is a question. So clearly, if you look at it, you will see that one of the common solutions for this would be psi naught. It's a guess basically. Exponential, if I take some constant times exponential, I want a minus. So basically minus m omega, I'll take it as x square, m omega x square divided by 2h bar. If I take this assumption of a wave function, I'll see that this will satisfy my differential equation, where my c will be some sort of normalization constant. Okay. How do I determine wave function's normalization constants? We know one basic property, that if you take an integral of this wave function basically psi square is a probability. So if I integrate psi square across all space, I should get it to be 1. So I'll simply say that integral minus infinity to infinity mod psi naught square dx should be equal to 1. Okay. Now how can I find what is psi? Okay. So what I'll say is psi square, right? Psi square means basically the 2h bars will go. So what effectively I'll do is I'll say let u is equal to square. So u square is what I want. So basically m omega by h bar whole half x. Okay. If I assume this, my du is going to be equal to same thing, m omega by h bar to the power of 1/2 dx. Correct? This is my integral. Okay. Sorry. So now what I should have is this integral, I'll write it as minus infinity to infinity du. So I'll go here. So basically h bar by m omega whole thing to the power of half into c square exponential minus u square du equal to 1. Okay. So this basically, this integral is a very common integral. So if you know the exponential minus u square du is going to be root of pi. If I substitute, I'll effectively get c square is going to be c square into pi h bar by m omega whole to the power of half is going to be 1. That implies c is going to be m omega by pi h bar whole thing to the power of 4th root. Okay. So now, so this is my normalization constant. So effectively my psi naught, my solution, ground state wave function is this m omega by pi h bar whole thing to the power of 1/4 exponential minus m omega x square divided by 2h bar. This is my ground state wave function. I can plot it, I can do a lot of other things. I can analyze this. Okay, this is my ground state wave function. Any questions?
You written mass for the wave function. What is the significance of mass when it comes to photons?
Okay, the question was in the wave function there is a mass. what is the significance of the mass? Well, I would say that this mass is a legacy from the harmonic oscillator, simple harmonic oscillator. So effectively, if you talk of the quantum mechanical equivalent, we said mass, basically we removed the mass by introducing generalized coordinates. So if you look at it in terms of generalized coordinate, okay, I don't know where to write this, so I'll write it. Okay, I'll put it here in the bottom. So Q is basically going to be, we define it as root m times x. Okay, so if I don't want to put the mass, which of course doesn't make sense, for light to have mass is not possible. Mass is 0, everything goes to 1. That's all. C, that's it, right? Constant wave function. So effectively, if you want to write in generalized coordinates, I would say you should write psi naught equal to, well, what happens to the coefficient? Again, it's a question mark. Okay, we'll have to see that. But effectively, this is going to be exponential minus omega q square divided by 2h bar. That will be the exponential term. Now, what happens to the mass in the coefficient? So we'll have to start with, essentially taking the generalized coordinates and solve it. You could also do that. When we have the generalized coordinate, we gave an expression for Q and P. So from that, if you solve, you will not get that. So otherwise, yeah, the mass is, wherever you see the mass, effectively you should put it as, Q, root mass into x is going to be Q. That's a generalized coordinate, right? And from there we get the quadratures. So Q actually had the electric fields. So in terms of electric field, you'll get to that. Okay. It's a very interesting question. I think we should really, yeah. Okay. So yeah, this was an aside. And last thing I want to cover, I'm sorry, this is getting too congested. Last thing I want to look at is, you see that what happens Hamiltonian, when Hamiltonian acts on psi naught, what happens? Okay, well, okay, we can solve this. So essentially, we know that Hamiltonian can be written as A dagger A plus half psi naught. H cross omega is also there, right? This is how we gave a definition, right? When we derived this is the expression we gave for Hamiltonian. Okay. So now if you write like that, what happens? Now we know what is A dagger times this one, right? So basically this is going to be H cross omega A dagger A psi naught plus half H cross omega psi naught. So we know that this term is going to go to, this is 0. Therefore this is going to be equal to half H cross omega psi naught. Again, the same answer. If you apply Hamiltonian on the ground state wave function, you get the ground state energy eigenvalue, which is half H cross omega. It's making sense. Okay. So this is how the quantum harmonic oscillator can be dealt with. Okay. So before I close, I just have a last small exercise problem. This is a bit tedious. Okay. But I mean, if you think, you can actually verify. But just to go through the motion, you should try this once. So the question, the problem is to verify that this ground state wave function satisfies the Schrodinger equation. How will you verify that? Just to show you the equivalence of this and how messy the integrals can get, let's work through it. Okay. So what essentially we have to solve, satisfy Schrodinger wave equation means this essentially means this thing, no? It means that H acting on psi, or in this case psi naught, should give you E acting on E naught psi naught, where E naught is the energy eigenvalue of the ground state. So if I take the Hamiltonian and I act, the Hamiltonian acts on this wave function, I should get that, right? Now the question is, what is a Hamiltonian? We know Hamiltonian is given by H is equal to what? P square by 2m. What is P square? P is IH cross dou by dou x. So this should be minus H bar by 2m. IH cross twice, so H cross square minus IH cross into IH cross. So that will give you minus H cross square by 2m. This is P square dou psi dou by dou x. Dou square by dou x square, right? This is second integral. If I'm acting on the psi naught, let me put psi naught as well here. Acting on psi naught, this is going to be this equal plus half m omega square x psi naught. If you compute this, you should get half h cross omega psi naught. That is my eventual solution, because that's a ground state, right? We know that. So if it is satisfied, if it satisfies, of course it will. But how messy the integral gets is something that you can see. Or I'll always end up some mistakes in the terms. So first calculate this. I'll first do maybe dou psi naught divided by dou x. That is going to be equal to, okay, let me keep this. Well, okay, this is an exponential thing. I'll leave it in the terms of psi naught. So essentially the constant times exponential. So basically the exponential will come out, the derivative will come out. So minus m omega x by h bar into psi naught, right? This is my first derivative. Now the second derivative is going to be what? Dou square psi by dou x square is going to be equal to minus m omega by h bar into x into dou psi by dou psi naught, right? So this will be minus m omega x by h bar psi naught, right? This is the first term, and the second term is going to be equal to okay, second term is equal to minus m omega by h bar. X will vanish, right? Well, now we differentiated psi naught. This we got. Now I'll differentiate x. So basically this will be psi naught. So now this is going to be equal to minus and minus. So m omega square or m square omega square by h bar square x square psi naught minus m omega by h bar psi naught, right? So if I now substitute this back here into this, this is going to be, okay, there's going to be minus h cross square divided by 2m. So this is going to be minus h cross square by 2m into m square omega square divided by h bar square x square psi naught minus and minus plus okay, h cross square by 2m into m omega by h bar psi naught plus the third term is coming from the this guy. So half m omega square x psi naught. Okay. So if you see this, of course, the first and the second terms will cancel. Sorry, first and the third terms will cancel. So you'll end up with this equal to h cross will go there, m will go. So basically half h cross omega into psi naught. So clearly this h psi naught equal to this much. So this is my eigenvalue E naught equal to half h cross omega. So that means basically, therefore, the ground state psi naught satisfies the Schrodinger equation. All right. So that's it. This is messy integral. The operators were much cleaner. Simply taking, A acting on psi naught will give you 0, half h cross omega is what you got. Now this is the first one. Ground state. If you apply derivatives, basically A operator has so many of these, px and, x, right? A square or A dagger square, A dagger cube, A dagger to the power of 4. The moment you keep doing that, it gets more and more messy if you directly deal with the equations. So that way, the algebra that Dirac had developed is a very clean way of deriving solutions. See, what was, if you look at, try to make a parallel with the original particle in a box problem. You have a potential given, and then we solve for the energy eigenvalues and the wave functions. In a square, square with infinite potential, it's simple. Now, the potential is different. What is the difference? The potential now is this, this one, right? M half kx square, essentially. That is my potential. If you have that sort of a parabolic potential, not a simple square potential, that's a toy problem. This is a real problem. If you try to do this, this is how the harmonic oscillator potential will be. If you have such a potential and the quantum mechanical equivalent How will you solve it? So the wave functions is what we got. So we are able to quantize light, and we saw that it is consistent with everything that we have studied so far. All right. So this is a theoretical foundation. So I think I'll stop this for this. Any questions? All right. So I'll stop this here for this week. And then in the next week, I'll introduce what are known as number states. And I'll also try to revisit the coherent states. And if there is some time, I'll just quickly tell you one application of quantum photonics, which is, what we call as quantum key distribution. That's, already implemented in some way. There are some commercial devices based on this. I'll tell you the motivation for it, and I'll give you a snapshot of what applications can be. Of course, there are a lot of problems. We will deal with it in the next week. Okay, and we'll just give you a glimpse of it, and how nanophotonics can actually solve some of this. It is an ongoing research. We will briefly discuss. All right. So yeah, thank you so much for your attention. I'll see you in the next lecture. Okay. Take care. Bye.